Hi, I'm Justin Howe, and I'm a junior at Gunn High School in Palo Alto, California.
And I'm Amanda Howe, a senior at Aragon High School in San Mateo, California.
Our research investigates the effect of infrared excess on finding habitable planetary environments in solar-like Kepler systems. Prior to doing research, I always had an interest in astronomy. I fondly remember when I got my first telescope from the local Walmart. I would eagerly wait till dark to aim my telescope up into the night sky in my backyard, looking for anything that might seem interesting. However, before this research project, I hadn't really thought I would pursue research in the field. At that point, I knew I enjoyed two main things, mechanics and coding. I love the ways that physics and concrete equations could provide insight into such complex, yet abstract systems. I was also interested in the ways that we can use code to extrapolate useful information from seemingly abstract or insignificant data. Our research in astronomy was a surprisingly perfect blend of these two interests, as it duly complemented my skills in mechanics and image processing. Mechanics helps me understand the science of the research, while image processing experience informs my background on our IR-access investigations.
Like Justin, I shared similar childlike interests. Ever since I was a child, I'd wondered what resided out there in the universe. Aliens, water, or a new planet? Curiosity fueled me when I saw documentaries of Neil Armstrong taking the first step on the moon in 1969. Since then, I have followed space exploration through media channels, documentaries, and reading. 2 years ago, I started our astronomy research focusing on habitability and stellar environments. I initially spent time researching what makes Earth so different from the other planets in our solar system: an energy source for life, vast amounts of water, and suitable temperature. Habitability shows the potential of life somewhere else. As we face environmental devastation with humans destroying forests, extracting resources, and ignoring our carbon footprint, the eagerness to learn more about other projects that can sustain other life becomes ever more important. Our project evolved from just observing the environments of stellar objects to the discovery of debris disks. Throughout the process, I was able to improve my research and analysis skills in addition to my coding background. Prior to beginning our research project, we did some research on past work in the field. After the Kepler mission release, their data released 25 Planet Candidates catalog of 8,054 stellar objects, Susan Thompson published a list of 47 Kepler objects of interest host star candidates that lie in the habitable zone. To investigate the connection between excess infrared emission coming from planets and the existence of warm dust in the system, we studied Rodrigo Silva Sobrino's paper, which provided insight into how to detect and quantify significant levels of infrared excess emission indicative of a habitable environment.
As you can see, past research is extensive, covering all bases ranging from transit photometry investigations of potentially habitable planets, all the way to infrared detections of a sample of Kepler's stellar targets. However, there is still a significant discrepancy in the field that is not investigated, and that is the research of infrared excess detections in potentially habitable solar-like and planet-containing Kepler systems. In addition, there is little research in the way of identifying the proportion of Earth-sized planet-containing Kepler objects that are habitable.
Therefore, we investigate zodiacal dust, infrared excess, and debris disks. Interactions caused by asteroid collisions and comet tails deposit zodiacal dust, which is an indication of debris disks in the solar system. Kepler systems with notable infrared excess contain bright zodiacal dust as well. Zodiacal-like dust temperature often mirrors that of nearby exoplanets due to them often existing at similar distances from a given host star and making up debris disks. In our study, we investigate debris disks as they are an important component of planetary systems and excellent tracers of planet formation and evolution. Existence of debris disks likely indicates collisions among planets, asteroids, and comets in the planetary system, like the process in the solar system which produces zodiacal dust. Our research aims to search for high IR excess detections and confirmed habitable solar-like systems.
By the end of our research, we ended up investigating the IR excess levels in both the 47 target Thomson small planet candidate sample, as well as our own compiled 53 target Jupiter-sized planet candidate sample. For this small planet sample, we found 3 stellar systems with notable IR excess and a habitable planet: KOI 172, KOI 2418, and KOI 2650. In our large planet candidate sample, we found 6:
KOI 191, KOI 254, KOI 421, KOI 908, KOI 1549, and KOI 3013.
Our research findings were submitted to the 239th annual meeting of the American Astronomical Society and were accepted for oral presentation. We were also invited to present our results in the press conference.
Despite our thorough research, there's still a lot of room for improvement and growth. Currently, we use relatively small samples, which increases the chance of error. Future investigations can include larger samples, thereby allowing us to be more confident in our proportions. Furthermore, to an extent, we're still limited by the technology we have at hand. But with the James Webb Telescope surveying even more potentially habitable planets with greater precision, we expect to be able to further confirm our findings and potentially find other worlds just like Earth.
These results provide unprecedented insight into the proportion of Kepler stars in the KOI catalog containing a terrestrial planet that has significant IR excess, bringing us one step closer to understanding the perfect conditions that must come together to create a habitable planet like the one that we live on. Our investigation also allows us to be even more confident that we are not alone in this expansive universe. Learning about extrasolar environments is a humbling experience that made both of us find so much more appreciation for the rocky planet that we call home. As Earth's population grows and environmental devastation rocks the planet, limiting global warming to 1 degree Celsius is extremely necessary and urgent by 2050. Otherwise, vulnerable communities will be pushed to the edge by the effects of climate change. As we continue to the point of no return, the race to find ways to preserve our planet's habitability from an astrophysical lens must be prioritized. Though we cannot whiz around on a rocket and scour the universe for new worlds, our research on other potentially habitable planets brings us one step closer to learning how to preserve our Earth. Though studying exoplanets that are light years away from Earth may seem trivial, we can use that research to better understand the underlying reasons for Earth's climate crisis and create a reliable model to project climate change, which will help us predict future trends.